Thanks a lot, Giovanna, for the introduction. My talk is about what we do with the trapped ion-based experimental platform in Mainz. It's not so much about phases or phase transitions, as we still operate in the few body regime, but there will be some entanglement and quite a lot of dissipation. First, I'll describe the capabilities and working of our platform. Then I will talk essentially about something related to quantum computing, namely building blocks for fault-tolerant quantum error correction, and then I'll switch gears and talk about quantum thermodynamics, mainly the realization of a heat engine based on a single spin. Trapped atomic ions are quite versatile platforms for many areas of physics and quantum technology. So we confine ions in radio frequency traps, so they experience tight harmonic confinement along all spatial directions. Then these platforms allow for high fidelity state readout and high fidelity gate operations. Also, the qubit lifetimes are quite long, so lifetimes, T2 lifetimes of up to hours have been observed depending on the implementation. Then we also have quantum control of the harmonic oscillator degrees of freedom. I come to that later, and we can also add tailored dissipation or errors. And currently, these platforms undergo a maturation from the few body domain to mesoscopic systems, in the sense that it's not so easy anymore to tackle these systems by means of numerical simulations. So what you see here is a more traditional approach to trapped ion platforms or quantum computing in general. So this is a macroscopic Paul trap consisting of some macroscopic pieces of metal as confining electrodes. The ions are kept in the form of a string-shaped Coulomb crystal here in the trap. They're addressed by laser beams, which control all the operations such as cooling, readout, and gate operations. And state-dependent fluorescence can be collected and detected, for example, on a CCD camera or a photomultiplier. So this platform is obviously great and has produced great results so far, but it has limits in terms of scalability. So as we try to put more and more ions in this Coulomb crystal here, the crystal stability becomes limited. We have a spatial crowding of the ions, spectral crowding of the motional modes, and we cannot address these ions anymore. So a way to circumvent this limitation was proposed by the NIST group now almost 2 decades ago. So that's a divide and conquer approach, where rather than such a macroscopic trap, a segmented ion trap is used. So that's essentially an array of individually controlled electrodes, which can generate microscopic potential wells. Then small ion crystals, which can be well controlled by laser beams or other radiation, can be locally stored. And the ions can be reconfigured by means of shuttling operations. So here the control voltages on the electrodes are changed such that the ions move. They're reconfigured, and this way we can realize larger systems. So these segmented traps basically come in 2 different flavors. The one is multi-layer, 3-dimensional traps, which still bear a degree of resemblance to these traditional traps here. So these are composed of machined wafers, which feature individually controlled electrodes, and the trap we use here in Mainz is shown here in the upper left panel. So that's the workhorse traps in which we perform the experiments which I present later on. Then there's a second flavor of traps, which is surface electrode ion traps. Here the electrodes are arranged in a planar geometry, so still the fields can give rise to a confining quadrupole here above the surface. So this offers the advantage that lithographic fabrication techniques can be used, borrowed from semiconductor industry, and this in turn allows for much more complex trap structures, so more segments, smaller segmentation, and even complex structures. Here, as you see, junctions, such that ions here can be moved around in circular structures, but this comes at the price that the confinement here is less ideal, and these traps are somewhat harder to operate in practice. So here is a sketch of our specific architecture. As I said, we operate a one-dimensional segmented trap. Each electrode here can be supplied individually with really for programmable voltage waveforms. Then there's one zone where fixed laser beams are directed to. That's the laser interaction zone, where all the operations such as readout, cooling, and gate operations are carried out. And then the ions are between, for example, two consecutive gate operations. They're reconfigured, moved along this linear axis here, brought to the laser interaction zone in the right configuration, and then undergo gate interaction. So these shuttling operations here fall into different categories, as for example, simple linear movement here along the trap axis. And we can split and merge ion crystals by doing transitions between single and double wells. And we can also perform ideal swap gates by rotating ion crystals around. So this allows for efficient permutations of the sequence of storage here. Yeah? So now I explain the qubit of our choice, which is the calcium 40 plus spin qubit, which has a number of advantages, such as very simple atomic level structure, which you see here. So we typically start experiments by doing Doppler cooling on the S to P transition. Then we can initialize the qubit, which is encoded in the spin of the valence electron, which is aligned in an externally applied magnetic field. So it's essentially the Zeeman sublevels of the S1/2 ground state, and the qubit can be initialized simply via optical pumping. So this will be relevant later on in the second part. Then the harmonic oscillator modes can be cooled close to the quantum ground state by sideband cooling on a stimulated Raman transition. Then we can carry out quantum gates also by utilizing stimulated Raman transitions. And of course, we need to read out the spin, which is not possible directly, but we can shelve population selectively from one of the qubit states to the metastable D5 state, which has a lifetime of about 1 second. So this can be done on this narrow electric quadrupole transition here. And then in the next step, we again use the resonant light driving the S2P transition for detecting resonance fluorescence. So we will detect resonance fluorescence if the ion has not been shelved to the D5 state. This is equivalent to a projection to a spin down state. And if the ion is detected in dark, this is equivalent to a projection to spin up. So the most complex operation on our architecture is driving entangling gates. So I'm going to explain that a little bit. So what you see here is the collective vibrational modes of a 2-ion Coulomb crystal, either along the alignment axis of the crystal or transverse to that direction. So you see for each direction, there's one in phase and one out of phase vibrational mode. And the key point here is that due to the Coulomb repulsion between the ions, all these modes become degenerate in frequency. So this is the way how a strong Coulomb interaction can be transformed into an effective spin-spin interaction. So this interaction is in turn generated again by laser beams. So here we use the Lin per Plin configuration of laser beams with an effective K vector aligned perpendicular to the trap axis. These beams give rise to a standing wave field here in this direction. And if the polarizations are chosen appropriately and the lasers are off present, this gives rise to an AC Stark shift, which depends on the spin and is varying spatially here along this axis. So now if we have a slight detuning between these two laser beams here, the standing wave will move here across the ion crystal, and the ions will experience an oscillating spin-dependent force due to the AC Stark shift. So we can resonantly drive motion selective to one of these modes here. So now, as I said, the AC Stark shift depends on the spin. So for example, if we want to excite this radial in-phase motion here, the force on the two ions is to point in the same direction, which means that also the spin has to be aligned in the same direction. Yeah? So only even parity spin configurations will be excited. So if we look at the harmonic oscillator mode in phase space, that's what we see here. the oscillating force is supposed to be detuned a little bit from the respective mode. So if we switch the force on, there will be transient displacement building up, but at some point the drive will become out of phase with the motion. So we will de-excite again at some point. We are back to the origin. There's no motion anymore, but the respective spin configurations will have acquired a geometric phase, which depends or which is given by the area here under these trajectories. And this phase is only accumulated by the even parity spin configuration. So what we generate is this entangling phase gate here. And this phase gate in turn can, for example, be transformed into a C0 gate by complementing with additional local rotations. So that's how we do our entangling gates. Then let me dwell a little bit on the shuttling operation. So I could talk about this for hours, but I'll make it short. And what I try to point out where the difficulty lies in realizing this or in operating this architecture. Yeah. So what we do, for example, is a simple shuttling operations where we move a single ion from one segment to the neighboring one in finite time, let it dwell for a fixed amount of time, and move the ion back to its initial location, and then spectroscopically probe the motion. So I'm not going to explain that, but by means of suitable spectroscopic methods, we can infer the mean phonon number on the particular mode, and the results you see here. So you see the mean phonon number versus the waiting time here on the target segment versus for different shuttling times. And as you see, the mean phonon number is actually modulated with this time, indicating that we pick up oscillatory excitation. So that's not surprising. What we do here is basically moving the support of a pendulum, and if we don't do it right, the pendulum will remain oscillating when the transport is finished. So why is this relevant? Because of the entangling gates. The feature of the entangling gates is that the drive coupling strength depends on the phonon number of the respective phonon number of the gate mode. So if the ion is oscillating throughout the gate interaction, the accumulated geometric phase will depend on the phonon number. There's a dispersion of phonon numbers, so there will be a dispersion of geometric phase, and therefore, in the presence of uncontrolled motion, the geometric phases will lead to effective dephasing. So that's actually the main error source of our architecture, and this means that the shuttling operations require a lot of control over the motions and a lot of elaborate calibration procedures. With these prerequisites at hand, I come to the realization of a building block for fault-tolerant quantum error correction by means of shuttling-based techniques. So what we work on for quite a time now is the implementation of a 7-qubit color code for quantum error correction. And this consists of 7 physical qubits arranged in a 3-plaquette geometry, and error correction consists in repetitively measuring these stabilizers here defined on the plaquettes, and that's done in the following way. So that's a circuit for measuring a parity or Z-type stabilizer on a 4-qubit data plaquette. It merely consists of 4 entangling gates, which flip the phase of the syndrome qubit by plus or minus pi/2. So that in the end, depending on the parity of the data qubits, you flip the phase of the syndrome, and you directly read out the parity in a QND manner. But this comes with a caveat, namely the gates themselves can introduce errors, and these errors then can be copied through following qubits by successive gates. That's what you see here. So these can then contaminate the register and deteriorate the efficiency of the quantum error correction code. But fortunately, there's a way to recognize and prevent that, and that's very resource efficient by simply introducing an additional so-called flag qubit, which undergoes 2 additional entangling gates with the syndrome qubit, and this serves as to intercept these errors here, which would otherwise propagate further through the register. And Essentially, we've been working now for 2 years to realize this very simple and innocent looking circuit on our shuttling based architecture, establishing all the required methodologies. So here you see how the circuit translates into a sequence of shuttling commands. Here the tiny spheres are ions, which are moved through the trap, brought to the laser interaction zones, where they undergo gate operations. So this really goes on for quite some time. There's a lot of shuttling. So as you see, this can become very complex. Yeah? And recently, we finally succeeded in making this work by removing all the roadblocks and improving the calibration procedures of the shuttling operations. So what you see here is a measurement of the bright probability of the final syndrome readout, indicating the parity of the data qubits. So the data qubits are initialized in all of the 16 possible logical basis states. And as you see, with a fidelity of about 90%, in the end, the syndrome qubit displays the right parity, and the additional flag qubit is mostly bright, which indicates that no error has occurred. So now we can post-select on the state, on the readout of the flag qubit, taking only the events into account where the flag has not been raised, indicated that no error has happened. And here, so it's barely visible, it's at the verge of statistical significance, but you see a trend that the match of the measured parity to the expected one has become better. So this indicates that this fault-tolerant error detection scheme actually works. And to make this more clear, we can go one step further and deliberately introduce an error on the syndrome qubit at this position here. So here's again these error propagation rules through the phase gates. So depending on whether we have an X or Y error on the syndrome, this will result in a Z error on the flag, which is subsequently detected, but in a different type of error on the initial syndrome qubit. Yeah? And that's what we did here. So for example, if we have an X error on the syndrome qubit, the syndrome looks correct, but now the flag is raised, which shows that the error is successfully detected. But if we introduce a Y error on the syndrome, also the syndrome is flipped with respect to the correct state. This indicates that without having the flag for error detection, then the parity would be exactly read out wrong. Yeah? So here the next steps will be to show that transient multipartite entanglement can occur within the circuit by introducing coherent errors deliberately on the syndrome that's currently in progress. So now let me switch gears to an experiment contributing to a field which some people like to call quantum thermodynamics. I prefer to call it microscopic thermodynamics, so that analyzes the thermodynamic behavior of single ion machines. And this sketch indicates that we have a heat engine where the working agent is a single spin 1/2, and this serves as to deposit in a work in a flywheel, which consists of a harmonic oscillator degree of freedom. Let me emphasize again that our trap ion platform has the specific advantage that we also have full coherent control over harmonic oscillator degrees of freedom. There's even various ways how to exert this control, which we scrutinize here. So these can be controlled by electric fields, optical forces, or even by coherent spin motion coupling. We can initialize harmonic oscillators close to the quantum ground state, and we can do full quantum state reconstruction. Yeah? So all of these things will be done here. So the spin heat engine works in the following way. We have a spin 1/2 ion confined in a harmonic potential and an additional optical standing wave, which gives rise to an AC Stark shift, as I've shown before. Now this standing wave is pinned, it's fixed such that the ion sits here at the node, and depending on its spin polarization, it experiences a force from the AC Stark shift, either pointing to the left or to the right. And additionally, we do optical pumping in an alternating way, synchronized to the period of the harmonic oscillator. So the spin polarization is oscillating at the harmonic oscillator frequency. So the spin-dependent force will be oscillating and the ion will gain oscillation amplitude here. So at first glimpse, this might look like an unnecessarily complex way to do resonant excitation, but what I will show you in the following, that this is actually equivalent to a 4-stroke Otto cycle and that fluctuations play a significant role here. So for a spin 1/2 working agent, it's somewhat clear that the Zeeman energy, including the AC star shift, is equivalent to the inverse volume of an ideal gas in a container, because for this system, the volume determines the energy spacing between the quantized levels, and we can also assign temperature to the spin, which is given by its expectation value. Yeah. So these are the prerequisites for making the analogy to the Otto cycle. So we have a spin 1/2 ion oscillating in the harmonic oscillator potential with the additional AC star shift potential. So we do an optical pumping, which is short as compared to the oscillation period here, which then provides isochoric heating. Then the ion oscillates from the right to the left. The energy spacing becomes smaller, so this would be isentropic expansion. Then we do optical pumping in the opposite direction, which is isochoric cooling. And then in the 4th stroke, the ion again goes from the left to the right. The energy spacing increases, so this is isentropic compression. So this is a perfectly justified analogy to the Otto cycle, but the interesting feature here is this is the most microscopic system which you can think of, namely a 2-level system. So the operation of this heat engine will be subject to quantum projection noise, because that's a 2-level system. Yeah. So now how do we do this in practice, and how do we finally probe the energy deposited in the motional degree of freedom? So and the experimental cycle looks like this. We cool the ion to the ground state, initialize the spin. Then we do the alternating optical pumping for a fixed time with the optical dipole force switched on. So that's the operation of the heat engine. And then after that, the spin changes its role from the working agent of the heat engine to a probe of the state of the harmonic oscillator. So how does this work? We again initialize the spin, then we perform a sequence of electrical kicks, which introduces a controlled displacement. And then finally, without going into detail, we can read out the remaining population in the ground state of the harmonic oscillator. So the quantity we obtain in the end is this one. Yeah, so rho is the state of the harmonic oscillator after heat engine operation. Then this is the additional controlled displacement by the electrical kicks, which does not depend on the spin. That's the ground state probability here. So what we measure is the Husimi-Kano Q function. Yeah, and this value of alpha here can be scanned by scanning the duration and phase offset of the kicks. Yeah. So here you see the Husimi-Kano Q function without operation of the heat engine. So that's basically the ground state. And with increasing operation time of the heat engine, we see increasing displacement, but also the size increases due to thermal fluctuations, and there's some additional squeezing here. So here, that's the results, the final results, which we obtain from statistical characteristics of the Q function. The deposited energy in the flywheel is increasing with the heat engine operation time. And what we can also extract, and that's the interesting part here, from the data is a quantity called ergotropy. So for those of you who have never encountered this, this is basically the equivalent of Helmholtz free energy in the microscopic domain. So that's the energy which can be extracted from a quantum system by means of a cyclic unitary, so the useful energy stored in the system. Yeah, and we see that the ergotropy here is always smaller as compared to the deposited energy, and the reason for this is exactly that that there's work fluctuations because of the microscopic nature of the system. Yeah, so there's the optical pumping of the spin is always probabilistic, so there's shot-to-shot fluctuations of the stored energy, which imposes fundamental limits on the efficiency of such microscopic heat engines.
Ulrich,
yes.
So just wrap up.
Pardon?
Finish, please.
Yes, I finish. So that's some future projects. So we continue along the direction of microscopic thermodynamics by analyzing how heat leaks on few qubit systems can be detected with a sensitivity beyond the second law. We investigate the purification transition on minimal instance systems together with Shamir and Shane. And we also continue in the direction of fault-tolerant quantum error corrections. And specifically, we want to analyze the thermodynamic properties of such circuits, establishing links between error rates and the energy required by a quantum computer. So with that, I'll conclude and show you the people who actually do the work in the lab. And we obtain funding from the US, from the EU in the framework of the quantum flagship, and from the German Ministry of Science and Education. Thanks for your attention.